Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that since long we are carrying a series on chemical reactivity and mechanisms, and under this series so far we have conducted numerous lectures so that it becomes convenient for you to study your course material. Dear friends, taking the series forward, today we are going to discuss about the chemical reactivity of alcohols, and for this we are pleased to announce that we have again with us in our studios Dr. Vandana. As you all know that Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's take advantages from her experiences as she wrote various research papers and she continuously give inputs to the various papers and articles so that her knowledge could be disseminated. So once again I would like to say that let's have experience from her experiences and welcome our guest Dr. Vandana. Dr. Vandana, welcome to the EduSet lecture.
Thank you so much, ma'am. Hello viewers. Today in the series of chemical reactivity and mechanism, I will talk about the preparations and about the structure of alcohols. And today's lecture I have take the some highlights like introduction, classification of alcohols, isomers of alcohols, structure of alkanols, preparations of alcohols. In preparations, we have taken the preparation by hydrolysis of alkyl halides, by hydration of alkenes, by the reaction of aldehydes and ketones with Grignard reagent, reactions of esters with Grignard reagent, reactions of epoxides with Grignard reagent, reductions of aldehydes and ketones, hydrolysis of esters, and by the reaction of aliphatic primary amines with nitrous acid. So, first of all about the introduction, what is alcohols? Alcohols are the compound that contain one or more hydroxyl group attached to the saturated carbon atoms. Phenols are the compound that contain one or more hydroxyl groups but attached to the carbon atom of an aromatic ring. What are enols? Those which possess OH group attached to the carbon atom of carbon-carbon double bond. We know in the earlier lecture I have stated that enols have tautomerism. These are the structures of alcohol, phenol and vinyl alcohol. It is the methanol, it is phenol. Here you can see the hydroxyl group is attached to the aromatic ring and this hydroxyl group is attached to the carbon-carbon double bond, means vinyl alcohol and enol. Next point is the classification of alcohols. We can classify alcohols according to the number of hydroxyl group present in the molecules. If a alcohol contains one OH group, it is known as monohydric alcohols. If it contains two hydroxyl groups, it is dihydric alcohols and so on. In general, alcohols containing two or more hydroxyl groups referred as polyhydric alcohols. Dihydric alcohols in which both hydroxyl group are attached to the same carbon atom are generally unstable because they will lose a water molecule to form a carbonyl compound. However, several exceptions are there, like chloral hydrate. You can see the structure Cl3CCHOH ka whole twice, which is relatively stable. You can see the examples: ethyl alcohol, a monohydric alcohol; ethylene glycol, a dihydric alcohol; glycerol, a trihydric alcohol, as it contains 3 molecules of hydroxyl group. Open chain saturated monohydric alcohols are called alkanols according to the IUPAC system of nomenclature. Its general molecular formula is CnH2n plus 1 OH and they are represented as ROH, where R is the alkyl group. Alkanone are further classified as primary, that is 1 degree, secondary, that is 2 degree, or tertiary, that is 3 degree alcohols according to the hydroxyl group bonded to a primary, secondary or tertiary carbon atom respectively. They can also be represented as RCH2OH. When one R group is there, it will be 1 degree. When 2R group is there, 2 degree, and when 3R group are there, it is 3 degree alcohols. Here are the 3 examples for each category. This is normal propyl alcohol, this is isopropyl alcohol, and this is tertiary butyl alcohol, that is 3 degree alcohol. Now, isomers of alcohols. Alkanols and alkoxyalkane both have the same general formula. You know what are the isomers? Having same molecular formula but different structures are called isomers. So, they can be isomeric. For a given molecular formula, there can be more than one alcohol in addition to ethers. So, we can have more ethers in respect to the other group. However, methanol has no isomer. When we are taking the molecular formula C2H6O, we are having here the isomers ethanol, that is ethyl alcohol, methoxymethane or dimethyl ether. For the molecular formula C3H8O, we are having 3 isomers. First one is propane 1-ol or N-propyl alcohol, propane 2-ol when the hydroxyl group is attached to the second position, or isopropyl alcohol, and third one is methoxyethane, that is ether, ethyl methyl ether. For the molecular formula C4H10O, we have number of isomers. You can see butane 1-ol, we can also say it N-butyl alcohol, butane 2-ol or secondary butyl alcohol, and its enantiomer S enantiomer butane 2-ol S-butyl alcohol. So, it is 1 because these are the optical isomers, we will count it as 1. 2-methyl propane 1-ol isobutyl alcohol. Next one you can see is 2-methyl propane 2-ol, or you can see tertiary butyl, we call tertiary butyl group is there alcohol, 1-methoxypropane, methyl N-propyl ether, 2-methoxypropane and ethoxyethane. So, you can see total number of isomers are here how many? 1. It will be counted as 1 because these are the optical isomers, enantiomers, because these are the non-superimposable mirror images. 1, these termed as 1. So, 1, 2, 3, 4, 5, 6, 7. So, total number of isomers are, constitutional isomers are 7 while structural isomers are 8. Isomers having molecular formula C5H12O, number of isomers you can see here are pentane 1-ol N-pentyl alcohol, R-pentane 2-ol, S-pentane 2-ol, again these are the optical isomers, so they will be counted as 1. Pentane 3-ol, 3-methylbutane 1-ol, 3-methylbutane 2-ol, 3-methylbutane 2-ol, again optical isomers. Next one is 2-methylbutane 2-ol, this will be treated as 1, 2-methylbutane 1-ol, 2-methylbutane 1-ol, 2,2-dimethyl, 2,2-dimethyl propane 1-ol and 1-methoxybutane. Other isomers for the same molecular formula are 2-methoxybutane, 2-methoxybutane it is R, it is S, so optical isomers, 1-methoxy-2-methylpropane isobutyl methyl ether, 2-methoxy-2-methylpropane, 1-ethoxypropane and 2-ethoxypropane. So, here you can observe the total number of constitutional isomer are 14, 8 alcohols and 6 ethers, and total number of isomers including stereoisomers is 18. When we are considering these optical isomers as 1, this is called constitutional isomer. If you are talking total number of isomers, it will be 18 for the molecular formula C5H12O. Now, about the structure of alkanols, you can see the simple methanol, simplest alcohol. Here you can see carbon and oxygen having sigma bond. So, This carbon and this oxygen both are sp3 hybridized. The linear overlapping of this sp3 hybridized and this sp3 hybridized oxygen makes a sigma bond. Again, this sp3 hybridized oxygen make a sigma bond while linearly overlapping with 1s orbital of hydrogen to form a sigma bond. Here again you can see this is another sigma bond, one more sigma bond and one more sigma bond. About the bond angle, about this bond angle, about this bond angle, it is near to the tetrahedral, that is 109 degree 28 minute. But you can see this oxygen having two lone pair of electrons. This oxygen is sp3 hybridized, so total number of hybrid orbitals are 4. One hybrid orbital is used to make a bond with carbon, second one is used to make a bond with hydrogen. So we have two sp3 hybrid orbital which is occupied by the lone pair of electron. So oxygen here has lone pair of electron. Because of these lone pair of electron, this bond angle is somewhat disturbed. So we can say because of the repulsion of these electron pairs, the bond angle will be shifted from 109.28 minute to 108 degree bond angle. So this is about the structure of alkanols. Now the preparations of alcohols. We have number of preparations. First of all, we are taking the hydrolysis of alkyl halide. When alkyl halides are heated with aqueous NaOH, KOH or silver hydroxide, alcohols are formed. Primary alkyl halides undergo hydrolysis by SN1, substitution nucleophilic unimolecular mechanism, and the products formed are in good yield. Secondary alkyl halides undergo hydrolysis by SN2 mechanism and partially by SN1 mechanism because the carbocation, it is bimolecular substitution nucleophilic, it is unimolecular. They undergo dehydrohalogenation to some extent to produce some amount of alkene as side product. The hydrolysis of tertiary alkyl halides occurs by SN1 mechanism, but dehydrohalogenation takes place to large extent by both E1 unimolecular elimination and E2 bimolecular elimination mechanism to produce alkene as the major product. The yield of alcohol can be improved by carrying out the reaction with the dilute aqueous sodium carbonate or sodium bicarbonate. The order of reactivity for alkyl halide is alkyl iodide, then alkyl bromide, then alkyl chloride. Here are the examples. You can see when 1-chlorobutane treated with potassium hydroxide followed by hydrolysis to give butane 1-ol. This is 2-propane, 2-bromopropane. When reacts with sodium hydroxide followed by hydrolysis, it will give you propane 2-ol along with propene as side product. Another examples are here 2-bromo-2-methyl propane. When reacts with sodium hydroxide, it will give you 2-methyl propene as a major product and 2-methyl propane 2-ol as minor product. Iodomethane, when reacts with silver oxide, it will give you methanol because here iodine acts as a better leaving group in presence of silver oxide. Next preparation of alcohol is from hydration of alkenes. Hydration means addition of hydrogen as well as hydroxyl ion. Acid catalyzed means in presence of acid. Alkenes undergo hydration in presence of dilute sulfuric acid to form alcohols. The reaction is reversible. Alkenes that are not able to produce sufficiently stable carbocations undergo hydration only to a small extent. Alkenes capable of producing relatively stable carbocations undergo hydration satisfactorily. Here is the example. You can see 2-methyl propene. First of all give you a carbocation, this is your tertiary butyl cation, and when it is hydrolyzed by water molecule, it will give a better leaving group, that is OH2, and it will give you 2-methyl propane 2-ol. In less reactive alkenes such as ethylene can be hydrated by passing its mixture with steam through solid silica impregnated with phosphoric acid under 70 atmospheric pressure at 300 degree Celsius temperature. Here are the examples, both are the industrial preparations. Ethylene will give you ethyl alcohol, while propene will give you, in presence of tungsten trioxide, it will give you propane 2-ol. Next preparation is from hydrolysis of alkyl hydrogen sulfate. In this method, alkenes are first passed through the cold concentrated sulfuric acid to make it protonated, and the reaction mixture is then poured into excess water and heat when alkyl hydrogen sulfates are hydrolyzed to give alcohols. You can see the example, ethylene when react with hydrogen sulfate will give you ethyl hydrogen sulfate, and when excess water is there, it will give you ethyl alcohol. Two more examples are there. Propylene first of all give you isopropyl hydrogen sulfate, and on hydrolysis it will give you isopropyl alcohol. Isobutylene will give you tertiary butyl hydrogen sulfate first of all, and on hydrolysis it will give you tertiary butyl alcohol. So, this is an excellent method for the manufacture of alcohol, since alkenes are readily obtained by cracking of petroleum. Next is the very important preparations for alcohol is hydration by oxymercuration and demercuration process. Alkene first of all treated with mercuric acetate, we can write like this, CH3CO का whole twice Hg or Hg and in short form OAC in aqueous tetrahydrofuran to form an organomercury compound. In oxymercuration, water and mercuric acetate add to the double bond of alkene. This mercuric acetate group becomes bonded to the less substituted carbon of the double bond and hydroxyl group of the more substituted carbon. So, this reaction involves anti-addition, anti-Markovnikov addition. The organomercury compound is then reduced with sodium borohydride in basic medium to give alcohol by demercuration. This oxymercuration and demercuration is highly regioselective. What does it mean? Highly regioselective means addition of the groups to the double bond in stereospecific manner and as well as in selective manner. Means positive group will attach to which group and negative group will attach to which group. The oxymercuration and demercuration is followed by the anti-addition, that is anti-Markovnikov rule. These are the examples. You can see propene when reacts with mercuric acetate in presence of tetrahydrofuran, first of all it will give you addition product, that is 2-hydroxypropyl mercuric acetate, and this will then reduced by sodium borohydride in presence of sodium hydroxide to give the propane 2-ol along with sodium acetate. Another example is 1-methyl cyclohexene. Here again this will attach to this double bond in anti-Markovnikov rule. You can see that here hydroxyl group is attached and here mercuric acetate group is attached. This after reduction with sodium borohydride will give you 1-methyl cyclohexanol. So, hydrogen will attach to that group which is have less number of hydrogen atom. Next preparation is by hydration of hydroboration oxidation process. Alkenes undergo electrophilic addition with borane BH3 in tetrahydrofuran to form trialkyl boranes. The addition of a compound having hydrogen boron bond is called hydroboration. You can see the structure BH2H. Because of this boron, it will highly electropositive and it will electronegative. Hydroboration is again regioselective, means addition of this borane will take place stereoselectively as well as and anti-Markovnikov due to both electronic and steric factors. Trialkyl boranes on oxidation with hydrogen peroxide in presence of aqueous sodium hydroxide yields alcohols. The addition occurs in a single step, that is concerted addition through a 4-membered cyclic transition state, hence it is called syn addition. Diborane and alkyl borane must be used carefully as they ignite spontaneously in air. So, they have to be used in an inert atmosphere. A solution mixture of diborane and tetrahydrofuran is less sensitive to air. These are the examples. You can see propene when reacts with boron hydride in presence of tetrahydrofuran, it will give you tri and propyl borane, and when it reduced by hydrogen peroxide, it will give you propane 1-ol. Another example is there, 1-methoxycyclohexene first of all will give you this addition product by borane by syn addition, and followed by reduction with hydrogen peroxide, it will give you trans 2-methyl cyclohexanol plus minus, that is both the enantiomer were formed. The overall result of hydroboration oxidation of an alkene is the syn addition of elements water to the double bond, that is it is a anti-Markovnikov manner. Primary alcohols can be compared by this method, thus this method is complemented to all the above mentioned method of hydration which do not yield primary alcohols except ethyl alcohols. Next preparation of alcohols is by the reaction of aldehydes and ketones with Grignard reagent. You know aldehydes and ketones give nucleophilic addition reaction. So, Grignard when reacts with aldehyde and ketone in nucleophilic addition mechanism, it will give you alcohols. Alkyl, aryl and vinylic halides react with magnesium in dry ether or tetrahydrofuran to form corresponding organomagnesium halide, that is RMGX. You are very much aware of the structure, this is called Grignard reagent. These are very powerful nucleophilic reagent because carbon magnesium bond is so strongly polarized that the carbon atom in this bond behaves like a carbanion because of the electropositive nature of magnesium metal. Aldehydes and ketones undergo nucleophilic addition with Grignard reagent in dry ether or tetrahydrofuran to form alkoxymagnesium halides as adducts. We can also say it halomagnesium alkoxides. The later on treatment with water or dilute acid, for example HCl or H2SO4 to give alcohols. You can see the reaction, this is the carbonyl group. Because of this electronegativity difference, oxygen has negative charge delta and carbon has delta positive charge. This is Grignard reagent. Because of this electropositive character, this R group will be treated as carbanion. So, this group will attack to this carbonyl carbon because of electromeric effect and added as nucleophilic addition to give this addition product. It is your halomagnesium alkoxide which on hydrolysis will give you alcohol. Primary alcohols are prepared by the reaction of formaldehyde with Grignard reagent. This is formaldehyde. When it reacts with ethyl magnesium bromide, it will give you this addition product which on hydrolysis will give you an propyl alcohol. Secondary alcohols are prepared by the reaction of aldehydes other than formaldehyde. You can see the example acetaldehyde CH3COH. When reacts with methyl magnesium iodide, there is a addition product which on hydrolysis will give you secondary alcohol, that is isopropyl alcohol. Tertiary alcohols are obtained by the reaction of ketones with Grignard reagent. Again the methyl magnesium iodide, when react with acetone, it will give you addition product, which on hydrolysis will give you tertiary butyl alcohol. So, it is a tertiary alcohol as 3 groups are there, R groups other than hydrogen. Next preparation for alcohol is reaction of esters with Grignard reagent. Secondary alcohols having 2 identical alkyl groups can be prepared by the reaction of ester of formic acid with the 2 moles of Grignard reagent in dry ether. The formic ester reacts first with 1 molecule of Grignard reagent to form an unstable adduct which eliminate a molecule of alkoxy magnesium halide to yield an aldehyde. The aldehyde reacts with another mole of Grignard reagent to give a secondary alcohol. This is the example. You can see this is the ester ethyl formate HCOOC2H5. When this methyl magnesium iodide attack to this carbonyl carbon because of the electronegative difference, first of all it will give you the addition product alkoxy magnesium iodide. Then by elimination of this group it will give you acetaldehyde, which again reacts with Grignard reagent, that is methyl magnesium iodide, to give the another addition product, which on consequently hydrolysis will give you isopropyl alcohol. So, you can see it is secondary alcohol because 2 R groups are there. Next example is the ethyl propionate, another one ester when reacts with methyl magnesium iodide will give you addition product. By elimination of this molecule, this alkoxide, it will give you butane 2-one, which on further reaction with another molecule of methyl magnesium iodide will give you addition product followed by hydrolysis to give the 2-methyl butane 2-ol, that is tertiary pentyl alcohol. It is your tertiary alcohol as 3 R group are there attached to the carbon which is having hydroxyl group. Tertiary alcohols having at least 2 identical alkyl groups can be prepared by the reaction of esters of carboxylic acid other than formic acid. You can see here with the 2 molecules of Grignard reagent in dry ether. The extraction takes place in a similar manner as above expect, that a ketone is produced and as an intermediate instead of an aldehyde. You can see the intermediate is ketone. Next preparation is by the reaction of epoxide. We have explained in our earlier lecture what are the epoxides. 3-membered cyclic ethers, 1, 2, 3. 3-membered cyclic ethers are epoxides, or we can also say oxiranes, or we can also say ethylene oxide is the simplest epoxide. Epoxide react with nucleophiles to undergo ring opening because of this ring strain by SN2 mechanism. When ethylene oxide is treated with a Grignard reagent in a dry ether, it undergoes ring opening to form a halo magnesium alkoxide. This is the example. Methyl magnesium iodide when reacts with ethylene oxide, it will give you addition product. This is your addition product, which on subsequent hydrolysis will give you propane 1-ol. With water or dilute acid, it gives a primary alcohol. You can see it is a primary alcohols, but the point to be noted here is that alcohol contains 2 more carbon atoms than the Grignard reagent. When a ring substituted epoxide reacts with Grignard reagent, you can see here now these 2 carbon atoms are not symmetrical, these are asymmetrical. This is CH2 group and this is the 2 substituted methyl groups are there. So, where it should attack the less hindered epoxide carbon. Here this is the less hindered, as this carbon atom contains 2 methyl groups, so sterically hindered. So, this phenyl magnesium bromide attack to this carbon atom to give the additional product, which on hydrolysis will give you 2 methyl 1 phenyl propane 2-ol. So, which kind of alcohol is here? 1, 2, 3. tertiary alcohol is there. Another preparation for alcohol is the reduction of aldehydes and ketones. Primary and secondary alcohols can be prepared conveniently by the reduction of aldehydes and ketones respectively. You can see this is the aldehyde which on reduction will give you primary alcohol, while ketone will give you secondary alcohol. The reduction can be achieved by a number of reducing agents. The most commonly reducing agents are lithium aluminium hydride and sodium borohydride. First of all, we are taking the reduction of catalytic hydrogenation, means in presence of a catalyst. Aldehydes and ketones can be reduced with hydrogen gas in presence of finely divided metal catalysts such as ranitidine or Adams catalyst, that is platinum oxide or palladium charcoal, to yield primary and secondary alcohols respectively. The unsaturated aldehydes and ketones are reduced to saturated alcohol because carbon-carbon double bond and triple bond are more susceptible to the catalytic hydrogenation than carbon-oxygen double bond. These are the examples. Propionaldehyde, when reduced in presence of ranitidine, will give you N-propyl alcohol, and this ketone butane 2-on will give you butane 2-ol. So, it is primary alcohol, it is secondary alcohol. Another example, 3-cyclohexenyl methyl ketone when reduced in presence of platinum to give you cyclohexyl ethanol, and 2-cyclohexene carbaldehyde in presence of palladium and charcoal will give you the cyclohexane carbaldehyde on selective reduction. Another reduction is with lithium aluminium hydride. Aldehyde and ketones are reduced to 1 and 2 degree alcohols respectively, as we have already stated. Lithium aluminium hydride is a powerful reducing agent and is capable of reducing many different functional groups. However, it does not reduce carbon-carbon double bond and triple bond. If a phenyl group is attached to the beta carbon of a alpha beta unsaturated carbonyl compound, both the carbon-carbon double bond and carbonyl group are reduced. Here are the representation. You can see it is the ketone when reduced with lithium aluminium hydride. Lithium being more electropositive than aluminium occupy this positive charge and will give you this addition product, which on reaction with hydrogen sulfate will give you 2 degree alcohol. This is the mechanism. Each step will involve the transfer of a hydride to the carbonyl group. You can see in the mechanism, this is your lithium aluminium hydride. There is a transfer of hydride to this carbonyl carbon. It will give you the addition product. Another molecule of ketone will add to this, will give you the another addition product. Again there is a addition of product, and which on hydrolysis by dilute acid will give you secondary alcohol. These are the examples. Propanol when react with lithium aluminium hydride followed by hydrolysis will give you propane 1-ol. This is primary alcohol. 4-tertiary butyl cyclohexanone 1, 2, 3, 4. When reduced with lithium aluminium hydride followed by hydrolysis will give you the 4-tertiary butyl cyclohexanol. It will be 90% in yield, and this is your cis 4-tertiary butyl cyclohexanol. It is your 10% and it will be less stable. Another example is cyclohexanone will give you cyclohexanol 4-methyl 1, 2, 3, 4. 4-methyl pent 3-ene 2-on when reduced with lithium aluminium hydride followed by hydrolysis will give you 4-methyl pent 3-ene 2-ol. This plus minus will show you the optical isomers, that is R as well as S. Cyclohex 2-enone when reduced with lithium aluminium hydride followed by hydrolysis will give you the optical isomers of cyclohex-2-enol, and when trans-but-2-enol reduced with lithium aluminum hydride followed by hydrolysis will give you trans-but-2-ene 1 2, second position पे double bond, but-2-ene 1 all. Another example is 3-phenyl propenol, because 1 2 3 at 3 position there is a double bond. It will reduce by lithium aluminum hydride followed by hydrolysis to give a primary alcohol, that is 3-phenyl 1 2 3 3-phenyl propane 1 all. So these are the examples which reduced with lithium aluminum hydride to give alcohols. Another preparation for alcohol is reduction with sodium borohydride. Like lithium aluminum hydride, sodium borohydride also reduces aldehydes and ketones to alcohols by the transfer of hydride ion to carbonyl carbon, as we have explained in earlier also. The reduction with sodium borohydride is more advantageous because it is a milder reducing agent than lithium aluminum hydride and does not reduce other functional groups including carbon-carbon double bond and triple bond. Moreover, the reaction is carried out in water or water-methanol mixture. Lithium aluminum hydride reacts with water violently and catches fire. So it is the drawback with the lithium aluminum hydride. This you can see ketone when reacts with sodium borohydride will give you addition product, and this addition product when hydrolyzed to give the secondary alcohol. These are the examples. Butanol will give you butane 1 all, butane 2-one when reduced with sodium borohydride will give you butane 2 all. These are the examples when these aldehydes and ketones reduced by sodium borohydride will give you the subsequent alcohol. For example, pent-3-ene 2-one 1 1 2 3, pent-3-ene 2-one will give you pent-3-ene 2 all, again optical isomers are produced. Para-nitrobenzaldehyde when reduced with sodium borohydride will give you para-nitrobenzyl alcohol. Cinnamaldehyde will give you cinnamyl alcohol. Methyl S 3-oxocyclopentane carboxylate will give you cis isomers as well as tris isomer when reduced by sodium borohydride in presence of methyl alcohol and followed by hydrolysis. These are methyl 3-hydroxycyclopentane carboxylate. You can see the mechanism. The mechanism is says, as we have explained in case of lithium aluminum hydride, there is a transfer of proton from borane to the carbonyl carbon, there is a addition product. Again one more molecule will add to this and will give the addition product. 4 molecules are there which on hydrolysis will give you the alcohols, secondary alcohols. Next reduction is with sodium and ethanol. Aldehydes and ketones can be reduced to alcohol by treating them with sodium and dry ethanol. When we are taking these two, this is called Bouvelt-Blanc reduction. The reduction that are affected by an electropositive metal, here we are taking sodium, and a suitable proton donor are called dissolving metal reductions. Here are the examples. You can see here we are taking this aldehyde propanol, sodium metal electropositive, and this is proton donor ethyl alcohol. First of all, it will give you the addition product. This is the sodium addition product, sodium propoxide, which on hydrolysis will give you propane 1 all, that is primary alcohol. Here you can see this is a ketone. When reacts with metal sodium and ethyl alcohol will give you addition product, and which on hydrolysis will give you the optical isomers of butane 2 all. Next preparation by the reduction with aluminium isopropoxide in isopropyl alcohol. Aldehydes and ketone can be reduced to alcohol by heating them in isopropyl alcohol in presence of aluminium isopropoxide. This reduction is called Mirvin-Pondorf-Verlet reduction. It is a specific for reduction of aldehydes and ketone because it reduces the selective carbonyl group of a compound containing other reducing group also, for example carbon-carbon double bond and nitro group. Here you can see this is ketone when react with isopropyl alcohol in presence of aluminium isopropoxide will give you secondary alcohol. This is the cinnamaldehyde will give you cinnamyl alcohol when reduced by this aluminium isopropoxide. Orthonitrobenzaldehyde will give you orthonitrobenzyl alcohol. So, you can observe here this group will be reduced. Selective reduction is there with the help of aluminium isopropoxide. What is the mechanism of Mirvin-Verlet-Pondorf reaction? The reduction occurs by a transfer of hydride ion from aluminium isopropoxide to the carbonyl carbon through a 6-membered cyclic transition state. You can see in the graphic representation that there is a hydride transfer. There is a hydride transfer from this aluminium isopropoxide to the carbonyl carbon through a 6-membered 1, 2, 3, 4, 5, 6. 6-membered transition state because formation of bond and breakage of bond takes place simultaneously. That is why we are stating here it is cyclic transition state, 6-membered cyclic transition state to give this addition product because this is ketone and we know aldehyde and ketones give addition product, nucleophilic addition product which on reaction with dimethyl alcohol will give you the secondary alcohol along with aluminium isopropoxide. Next reduction is with carboxylic acid and esters. Reduction with aluminium, lithium aluminium hydride. Carboxylic acid and esters are reduced to primary alcohols when they are treated with lithium aluminum hydride in dry ether or tetrahydrofuran and subsequently acidified with dilute acid. Lithium aluminum hydride reduces many functional groups but does not reduce this double bond and triple bond. You can see the example. This is your 4-methyl pent-2-enoic acid because double bond is attached to this carboxylic group, and you can see this lithium aluminum hydride will reduce this carboxylic group only and it is not reducing this carbon-carbon double bond. So, here we are having the product 4-methyl pent-2-en-1-ol. More examples are here. Benzoic acid will give you benzyl alcohol. Cinnamic acid will give you 3-phenyl propane 1-ol. Methyl propionate will give you propane 1-ol. Methyl pent-2-enoate will give you pent-2-en-1-ol. Ethyl 3-oxobutanoate will give you butane 1,3-diol in optical isomers. Esters are reduced to primary alcohols by treating them with sodium and ethanols. You can see this is the ester when treated with sodium in presence of ethyl alcohol will give you primary alcohol. We have already stated this is your bivalent blank reduction. These are the examples. Methyl butanoate will give you butane 1-ol and ethyl decane dioate will give you decane 1,10-diol. Next reduction is with reduction with the diborane and lithium borohydride. Diborane, that is B2H6, reduces both carboxylic group and esters to primary alcohols. The carboxyl group is much more readily reduced than the ester. So, here selective reduction is there with diborane. Lithium borohydride does not reduce carboxylic group but reduces ester group. Again, here is selective reduction of ester group to the primary alcohol in presence of carboxylic group. Sodium borohydride does not reduce either of the carboxylic group and ester groups. So, you can see in this reaction, this is your S5-methoxy 3-methyl 5-oxopentanoic acid, or we can say S-methyl 3-methyl glutarate. When reduced by diborane, it will reduce this group to the alcoholic group, and when it is reduced by lithium borohydride, it will reduce this group to give the alcohol. So, you can see this carboxylic group is reduced by the diborane and this ester group is reduced by lithium borohydride. So, selective reduction is there with the help of different reducing agent, which on subsequent hydrolysis will give you the 5-methyl 2-oxacyclohexanone S and R 5-methyl 2-oxacyclohexanone. Next preparation is by the hydrolysis of ester. Esters are hydrolyzed by heating with aqueous alkali to yield the corresponding carboxylate salts and alcohols. The carboxylic acid is obtained by the acidification of reaction with HCl or H2SO4. You can see the reaction, this is the ester group. When reacts with sodium hydroxide in presence of heat and water, it will give you the salt of carboxylic acid along with alcohol. This sodium carboxylate when react with HCl will give you the carboxylic acid. Here is the example, when ethyl propionate reacts with sodium hydroxide in presence of water and heat, it will give you sodium propanoate along with ethanol. The hydrolysis of esters with alkali is called saponification because the method is used in the production of soaps from fats. This is the mechanism. The reaction involves nucleophilic substitution at acyl carbon by an addition elimination mechanism. If you remember the lecture about the carboxylic acid derivatives, this is the derivative of carboxylic acid, means this is the ester. This OR is substituted by OH group. So, this ester carboxylic derivative undergo nucleophilic substitution reaction, or we can say addition elimination mechanism here. First of all, this hydroxyl group will attack to this carbonyl carbon because of the electronegativity difference. This carbon will occupy the positive charge and will give you the intermediate addition product. This is the tetrahedral intermediate. This is on elimination of this alkoxy group R-O will give you this carboxylic group, and this will give you the carboxylate ion, which is stabilized by the resonance. So, we can say ethyl propanate labeled with oxygen 18 in the oxygen of ethoxy group demonstrates the acyl oxygen bond cleavage in the reaction. You can see in the reaction, this oxygen is labeled with the number that is 18, and in the product you can see this where this oxygen goes. This goes to the alcohol, and this is the sodium salt of carboxylic acid. Acid catalyzed hydrolysis. Esters are also hydrolyzed by heating with dilute aqueous H2SO4 to give carboxylic acid and alcohols. The reaction is reversible and requires a long period to attain the equilibrium. You can see the example, ethyl benzoate will give you benzoic acid. On the other hand, hydrolysis of esters with alkali is almost irreversible because the product carboxylate ion is highly stabilized by resonance. This is the mechanism. Acid catalyzed hydrolysis of esters also involves nucleophilic substitution at acyl carbon by addition elimination mechanism. In this mechanism, you can see that first of all there is a protonation of this carbonyl group, that is this proton will attach to this oxygen being electronegative being having 2 lone pair of electron. So, now we are having the protonated esters, and to this protonated ester a water molecule attack to this carbonyl carbon, because the electropositive character of carbon is increased by the attachment of this hydrogen to the oxygen. So, here we are having the addition product, and this water molecule will attack to this hydrogen, and there is a elimination of this product. So, here we are having tetrahedral intermediate, which on elimination of water molecule to give this addition product. Here you can see this proton is attached to this oxygen and it is taken up by the water molecule to give the carboxylic acid. The acid catalyzed hydrolysis of esters also involves acyl oxygen bond cleavage. Again you can see where this oxygen goes. It goes in this succinic acid from this water molecule. So, there is a cleavage of acyl oxygen bond. Aliphatic primary amines react with nitrous acid at 0 to 5 degrees Celsius to form alcohols. Nitrous acid is relatively unstable. It is prepared in situ, that is within the reaction, by the reaction of sodium nitrite with dilute HCl or sulfuric acid at the temperature 0 to 5 degrees Celsius. Here is the example, ethyl amine will give you the ethyl alcohol. Alcohols are usually not prepared by this method because several side products are formed. You can see these are the side product, nitrogen, sodium chloride and water molecule. So, the reaction of propane 1 amine with sodium nitrite and dilute HCl yields a mixture of propane 1-ol, propane 2-ol, propene, cyclopropane, 1-chloropropane and 2-chloropropane. So, we can see in this preparation of alcohols, number of side products are there. This is the mechanism, how mechanism proceed. First of all, there is a preparation of nitrous acid by the reaction of sodium nitrite and HCl. This will give you the nitrosonium ion. This nitrosonium ion will attack to this 1 degree primary amine, 1 degree or primary amine to give this addition product, and which will give you this nitroso addition product or hydroxyl addition product, and which will give you unstable this RN2, which will give you alcohol. So, alkyl cation R plus formed by the dissociation of RN2 because it is highly unstable, and which may give several substitution and elimination products which may involve carbocation rearrangement. Certain cyclic amines can undergo either ring expansion or ring contraction reaction on treatment with nitrous acid. These are called Demianov rearrangement. You can see this amine, cyclobutane amine, when reacts with nitrous acid will give you the primary alcohol along with this alkene and with these side products. Another example is there. So, cyclopropyl methanamine on reaction with the nitrous acid gives the same product mixture in the same proportions as in the reaction of cyclobutyl amine. So, the summary of the lecture is we have discussed about the introduction of alcohols, what are the alcohols, about the classification like monohydric, polyhydric, 1 degree, 2 degree or 3 degree alcohols, about the isomers possible for a particular molecular formula, about the structure of alkanols, about the preparations of alcohols from hydrolysis of alkyl halides by the hydration of alkenes, by the reactions of aldehydes and ketones with Grignard reagent. We have studied by the nucleophilic addition of Grignard reagent, that is RMGX, with aldehyde and ketones we can produce the alcohols, by reactions of esters with Grignard reagent, by the reactions of epoxide with Grignard reagent, by the reductions of aldehydes and ketones with number of reducing agent For example, lithium aluminium hydride, lithium borohydride diborane with the dissolving metal in ethyl alcohol, by the hydrolysis of esters, by the reactions of aliphatic primary amines with nitrous acid. So, we have discussed about all the preparations of alcohols. In the next lecture, we will discuss about the reactions of alcohols. Thank you.
With this note, thank you ma'am, thank you so very much, and I would like to tell you all that Dr. Vandana would be again with us tomorrow, and we would be discussing more as she has herself discussed. So dear friends, if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cec@nic.in, and for accessing this lecture you have YouTube, with the help of which you can access this lecture, as we daily upload lectures for you, so that it becomes convenient for you to see these lectures ample of time. So once again, I would like to thank Dr. Vandana for giving her precious time as well as for giving precious inputs to this very lecture. Thank you ma'am. Thank you once again.